Добрый день, уважаемые коллеги! Рада приветствовать вас на нашем третьем вебинаре, который будет посвящен бассейновому моделированию в зонах со сложной тектонической обстановкой. Next slide, please. Сегодня я хотела бы представить этого спикера, Алсид Тибо. Я думаю, что многие из вас его уже знают. Специалист, который очень много занимается и давно уже Кроносом. Я думаю, что сможет ответить на все вопросы, которые у нас могут возникнуть в течение вебинара. Next slide, please. Во время вебинара звук будет отключен, поэтому если у вас будут какие-либо вопросы, вы можете их писать в течение всей презентации во вкладочке Questions, вопросы, соответственно. Все вопросы, которые будут озвучены, мы на них на все ответим. Даже если мы не успеем на какие-то вопросы ответить в течение презентации, мы обязательно пришлем вам в дальнейшем на почту ответы на них. Также у нас есть вкладочка Polls, где мы хотели бы задать вам несколько вопросов касательно самого вебинара, касательно качества звука. Вопросы будут появляться в течение вебинара, и по возможности попрошу вас на них ответить. Также по окончанию вебинара, приблизительно в течение недели, будет доступно видео на YouTube-канале полностью с нашим вебинаром, и в ссылочке мы вам направим каждому из присутствующих, соответственно, этот вебинар. Также, если у вас есть какие-нибудь там вопросы или предложения, или вы, может быть, хотели бы что-то обсудить, вы всегда можете написать нам на нашу почту info.moscow@bsip.com, задать все эти вопросы, позвонить по телефону или приехать к нам в офис в Москве, который находится на Вавилова. Мы вам все расскажем, покажем и, может быть, более наглядно какие-то вещи продемонстрируем. Thank you very much, Alsid. You can start.
Thank you. Okay, so hi everyone. So this is the agenda for the meeting today. So I will start the meeting by presenting the software, so KronosFlow. I will share with you the overall workflow from restoration to modeling, and I will try to show you the specificity and benefits of the tool. The second part of the presentation will be dedicated to some examples of applications in compressive and extensive settings. And finally, the last part of the meeting will be dedicated to a demonstration of the software. In between each sections, we will have a Q&A break where we will try to answer at best your questions. So first, let's have a look at the software. But before that, let's revise what is the classic basin modeling workflow. So usually, when you perform basin modeling, what you do is you first build your model at present day. So for that, you define the stratigraphy, so all the units that you will consider, the lithologies within these units, and the source rock information in the model. The grid is usually vertical pillar-based, and that means that the faults are not explicitly represented within the model. Once you have created that model at present day, you need to reconstruct the history of the basin through time. And this is done through a vertical backstripping. So everything is vertical. You just take into account the decompaction of the sediments, but you do not take into account the shortening or the extension of the basin. And finally, once that restoration is done, you can perform the forward simulation in order to compute the thermal history, the maturity of the source rocks, and the fluid migration, either water or hydrocarbon. And here as well, there is usually no specific fault modeling that is considered and taken into account. So here we see that this workflow has some limitations when it comes to handling complex regions that underwent a strong extensive or compressive regimes. So in that case, that type of structure, that type of geometry cannot be considered, cannot be taken into account, and that is problematic because we know that folding and faulting can have a critical impact during the history of the basin on the burial and the source rock maturity, on the hydrocarbon expulsion and migration pathways, and finally on the final accumulation, so the charge and fluids composition. So what do we do in order to be able to take that into account? What are the elements that we need to be able to consider? So first of all, we need to have a grid that can explicitly take into account the geological objects and their complexity. So we need to have a mesh that will explicitly consider the faults, and we'll have specific types of cells that can represent perfectly the geometry. So we can no longer have vertical pillars, but we need to have an unstructured mesh. Second, the movements along discontinuities and lateral displacements have to be accounted for. So that means that we have to replace the vertical backstripping by a step-by-step structural restoration that will properly consider the extension or the compression of the basin through time, and that will therefore properly represent the migration pathways through time. And finally, we need a new simulator in order to handle that type of mesh that I just presented, and also to properly model the impact of the faults on the fluid flow. So what is the new workflow that we propose in that context? So the first step of that workflow is to build the section at present day. So for that, we start from a balanced section and we consider all the units that are needed within the stratigraphic scale. So that means we have to consider all the units that will have an impact on the petroleum system. So we need to take into account the source rocks, the reservoirs, and all the layers that will have a petrophysical impact on the flow. Second, we perform the step-by-step backward restoration. So one step for each event of the restoration, where we take into account the erosions and the removal of each unit through time. Once that restoration is done, we can compute the mesh through time, and in that case, that mesh will be unique and continuously deformed. So it's a single mesh that follows the deformation through time. And once we have computed that mesh, we can perform the basin modeling forward simulation, where we actually define the petrophysical behavior of the lithologies, the source rock content, and we just compute the same way as before, the temperature, the pressure, the maturity of the source rock, and the hydrocarbon saturation. So in order to perform that workflow, we will use KronosFlow, which is a new 2D kinematic tool that was initially created to produce very easily and rapidly consistent geological scenarios, and for basin modelers initially, but it can also be used by structuralists. The key for that tool was to find the good balance between an acceptable kinematics and productivity. So we try to reach a time to perform the study that is good enough and that is short enough to comply with the industry standards. So in terms of technical quality and ergonomics, this is what we have to offer. So in terms of deformation solutions, we have some geometry-driven methods, which are the oriented shear, the flexural slip, the moving least square, and we have also some mechanic-driven methods, and in that case, it's the finite element methods. So the restoration will account for sediment decompaction, as we are able to take into account the lithology in every block of the model, and we will be able to account for erosion as well. As mentioned before, the ergonomic is a key element. So first of all, the deformation engine have a good performance. So they are very quick. They are almost instantaneous in their deformation. We have an automated detection and selection of sources and targets, and everything is mouse driven. So this is actually shown right here in that little video, where actually what you see is the deformation of one block. So you just move the block and then you simply drag and drop it to the location of where it should be, and the deformation occurs on the floor. So you have a direct deformation. And finally, we also have a kinematic scenario that tracks all the actions that were performed through time. So they allow for several things. First of all, they allow you to understand what was done. They allow you to test various hypotheses and to try new branches, new scenario from a given restoration step. So you can try, for example, a different erosion content. You can try a different paleobathymetry or something like that. So you can try various hypotheses. And also it will allow you to share that information with your colleagues because they will be able to track and to know everything that has been done. And it will also be for you a reminder of what you have done if you get back to that project a few months later. Once that restoration is performed, you will be able to compute that continuous grid, and that grid is actually unique because it is a single grid continuously deformed through time. So this is what you are seeing right here in that video. So actually what is interesting here is that you see that the faults are taken into account, but the grid is unique. It's the same grid that is deformed, and you can track every single cell through time. So you see that you have a deformation. And on top of that, the faults act as a juxtaposition interface, and all the properties are continuous across the fault plane. So the overburden, the temperature, the heat flow is continuously computed over the basin. So that means that you have a continuous computation, either spatially or through time. So there is no remapping, there is no regridding at every time step. It's just one unique grid through time. Once the grid has been performed, has been generated, you can define your lithology content, source rock content, and your thermal condition through time in order to compute classical properties like what is displayed right here. So the temperature, the thermal conductivity, the vitrinite reflectance, the transformation ratio, the saturation. So here you see that everything is computed in the model. So here we are switching from one property to the next, but everything is continuously computed. So this is, once you have generated the restoration, it's just a regular basin modeling that you can perform afterwards. On top of that very unique mesh, we also have a specific fault model. So as I mentioned before, the faults actually are just interfaces between the blocks. So this is what the user defines, and this is what the user sees. But actually, the model that is taken into account within the calculator is way more complex and way more advanced. So actually, that line right here corresponds to this fault model right here, which is composed by a core zone in purple here, a damage zone in orange here, and it is co-refined with the surrounding units. So here you see that the units actually enter into the faults in order to create these cells within the fault. So these are cells which have a volume and in which any property can be computed. So actually, how does that work? In every cell, actually, we have a pressure that is unknown and that needs to be computed. The users define a permeability and a capillary pressure in every unit of the model through the definition of the lithology content. And then you can tune the behavior of the fault through factors. So for example, you can define here the factor A and the factor B to control the permeability and the capillary pressure relatively to the permeability and the capillary pressure of the surrounding lithology. And so these factors here will control the way the hydrocarbon and the water can enter into the damage zone of the fault. So if the factor is above 1, that means that you assume that the fault is permeable. Here I'm talking about the permeability. If the factor is lower than 1, that means you assume that the fault is less permeable, so close to impermeable. And if the factor is 1, you just assume that the fault's behavior is the same as the surrounding lithology. You can then define the thickness of the damage zone and the factor C in that case in order to control the permeability along the fault and therefore control the movement of the hydrocarbons and the water along the fault, so on both sides of the fault. Finally, through the definition of the thickness of the damage zone and the factor D, here you can control the movement of the fluid flow across the fault through the core zone. So these parameters can, of course, vary through time and then can also vary from one fault to the next. So this is actually an example right here where we will see the impact of the fault. So this is passive margin offshore Brazil, where we will focus on that toe thrust here, where we have the movement of this block on top of this block right here. So in this case, the fault has been set to transparent, which means that the factors are set to 1, and it is just through the juxtaposition of the reservoirs with the movement of the fault that we will see movement of hydrocarbon from one side of the fault to the other one. So let's actually play that. So here you see that we start from a step where the hydrocarbon has already migrated at the top of the structure through a long distance migration. And then when the movement of the fault occurs, we can see that when we have a connection between the reservoirs, there is a transfer of the hydrocarbons from one side of the fault to the other. So here we see that we properly represent the movement of the hydrocarbon through time. We properly represent the geometry of the model through time, which is very geological, and the present day representation of the hydrocarbons that we obtain is the best one that can be. And of course, you can make various hypotheses very easily regarding the behavior of the fault. So here transparent, but you could as easily test a model that is impermeable or permeable with a migration along the fault. So this concludes the first part of the presentation, and I think we can have our first Q&A break if there are any questions to answer.
So, hello everyone. Actually, there is no questions for now, so don't be shy. We are here to answer your questions. Oh, so there is one now. How can we interpret fault parameters from fieldwork, seismic, and so on?
So that is a good question. This is always a bit tricky to understand the behavior of the fault. So regarding that aspect, there will be several ways of handling it. The first one is if you have an idea of the behavior of the fault, so through field work. So for example, if you have some analogs, or if you can see part of the fault, so if you can see if there is some cementation or not, or if you have some shell gauge ratio information, then you can just manually integrate that information within the editor. So this is what I will show you during the demo. But what you can do is you can define the factors. So for example, if you know there is cementation, and you know when the fault occurs through your geological understanding of the area, you can define a factor for permeability that becomes lower than 1 and tune that whenever you want in order to define the impact of the fault. If you do not have that information, that means you don't really know if the fault should be permeable or not. What you can do is simply test the different options and see what are the accumulations that you will represent for each scenario. And if you have an accumulation that you know should be there, if there is a field that is known in the area and you reproduce it in one case and you do not reproduce it in the other case, that means that one scenario is more relevant and is more correct than the other one.
And the idea of the full workflow is also to be able to test quickly many different parameters to reduce the risk. We have a second question. How do we do the quality control of the mesh around the faults? How many iterations can we have?
Actually, the mesh is usually, and you will see that during the demo as well, the mesh is usually very good from the beginning. So you will see that if you have your fault, the fault will be automatically taken into account within the mesh, and usually there is no problem. What you can do during the restoration, you can check if there is a gap that has been created by the deformation or not. But if you have corrected that gap, or if you have corrected that, it should be fine. If you want, you can also try various resolutions to see which one seems the best and which one represents your geometry the best. So you can try different parameters. And as the generation of the mesh is instantaneous, you can try that very quickly. So in 1 minute or two, you can try 5 or 10 different values for your resolution. Finally, you can have, as I said, some issues during the restoration. And if you need to correct that, you may need to go back to the quality of the restoration and correct some gaps or some things like that. And that may take a few minutes, but it's usually quick. So in a few minutes, or I don't know, at a very maximum 1 hour, you can have a mesh that is clean normally.
Yes, just to complete Alcide's answer, I'd say that the mesh creation is totally automatic, so you don't have anything to do. And for the fault internal mesh that is implicit in that we don't see, this is also automatically done through a co-refining of adjacent meshes. So basically, there is really nothing to do. The software handles it for you. Okay, we have another question, Alcide.
Yes.
The faults could be opened for some time and then closed. Is it possible to take into account in the software? So the answer is yes. You can really test whatever you want. So the fault can be transparent at the beginning, then, for instance, open when they start moving, and then become sealed and totally impermeable when they stop moving. If yes, how is it possible to interpret in the field lab, or can we only test it in the scenario? So it's a bit the same answer that Alcide gave you before, I think. If you have some data that tells you that the fault might be closed or open, then you can start by trying that out. But of course, you will be able to run several sensitivity tests in the application to see what works best for you. Olga, I think, or Katya, I think we need your translation here.
Okay, hello. So the question is, what is the detail of our modeling? Is it possible to do small fractions in terms of fractioning of the reservoirs, or is it possible to do just the bigger faults, regional one?
So yes, usually we work at basin scale, and so what we take into account are the main faults. The fractures within a reservoir can be considered, but it's only going to be considered through the permeability aspect of the lithologies. So you can actually tune it and change the permeability of your lithologies at a certain time when you assume there is going to be fracturation. So for example, if your effective stress becomes too big, you can change the permeability behavior and increase the permeability in that layer. But there is no direct representation of the fractures and a proper and direct modeling of their presence and their impact. So we are really working at big scale. If you want to work at reservoir scale, we actually have other solutions, which are FracFlow and PumaFlow, which is more for reservoir flow, and where you will be able to properly model the impact of the fractures at reservoir scale.
We have another question from Katya and Katerina. If we have to do some manual correction in the restoration, how much can we move points? What is the limitation of manual additions?
So yes, indeed, when you perform the restoration, you can either use an automatic method, so that I mentioned, flexural sleep or moving least square, stuff like that. So in that case, the entire volume will be automatically recomputed after the deformation. But if the deformation is not satisfactory, or if because of the present day interpretation, you have some errors in your geometry in the past, you can manually change it and modify the geometry of every single horizon or everything. Here, the difficulty, I mean, or the thing you need to keep in mind is that as the mesh is continuous, you need to be able to track the points through time, and you need to keep them in the right order. So here you can actually, technically, you can modify as many points as you want, but when you do that, you need to be careful that you keep the right spacing between the points, and you do not create any crossing or any problem like that. So of course, the more points you move, the more problems you may encounter. That aspect as well is also very dependent on the expertise of the user. If you are an expert user, you usually know how to avoid any problem. If you are a beginner user, it might become a bit trickier. So here I would say when you start with the software, it's better to use a very limited number of points. So maybe 10 at a maximum just to correct something, but avoid any mistake. And then when you become more familiar with the software and after a few months, once you have acquired a bit of expertise, then you can start moving what you want. And in that case, you can actually pretty much move whatever you want.
Yes, I will add to that reply, since Katya, you already know the software. In the coming version that is about to be released in June, there are some nice improvements to fix some issues you might have in the restoration, you know, such as big gaps or overlaps coming out of the restoration. With a simple click, instead of moving points, you just click on the issue and it's automatically fixed. And we are also working on better edition tools to allow you to move automatically, to redraw automatically a part of a polygon, like a big segment, from point A to point Z automatically. So this will be available soon as well, and it will for sure enhance a lot the addition of numerous points in one shot. And also we are working on improving the flexural slip method so that this kind of addition is should be less necessary. Okay, so lithological differentiation of the sequence. This is the topic. What is the level of details? Then, if sedimentation occurs during movement, is this taken into account? And then, what kind of traps do we have? Can we have structural traps and stratigraphic traps, lithologic traps? Is there any mechanism to model and evaluate those?
Okay, so that is
questions. Okay.
That's a very complete question.
So first one, just to recap on the lithology description and the level of details we can have.
Yes, so here you define as many units as you want. And within those units, you can define the lithology content, and the lithology content can vary laterally. So even within one patch, what we call a patch, which is delimited by the fold blocks, by the folds and the top and bottom of the unit, you can have a lateral variation of your lithology, and that lateral variation doesn't have to be vertical. You can have any geometry that you want, so you can very precisely draw the geometry of your layers and create a pinch out. For example, there is no problem at all with that. Regarding the sedimentation at the same time as the movement, that is taken into account. So actually you can have a movement of your blocks while the sedimentation occurs. You can have erosion in one area and sedimentation in another. The only limitation is that you cannot have sedimentation and erosion at the same time, which is also what occurs in real life. So it kind of makes sense.
The last last part is then the different types of traps, structural and stratigraphic.
So yes, so we can of course model both traps. So the stratigraphic traps will come from what I mentioned, the variation of lithology. So you can have a lateral variation and you can have a pinch out. So here you may block your hydrocarbons over here, depending on the variation of the lateral and vertical variation of lithology. And the structural traps just come from your geometry. And as you can see the evolution of the geometry through time, you may have some traps that will be created, deformed, recreated, and so on. And all that will be taken into account. Regarding the estimation of the lithologies, this is not done within ThemisFlow. So ThemisFlow, the lithology is considered to be an input of the software. So you just draw or define the lithology content at the beginning of the software. In order to estimate that lithology content, that has to be done through a different tool. So you can have various methods. So it can be an interpolation between your wells. It can be a seismic stratigraphy interpretation or seismic lithology interpretation, seismic characterization. Or you can, of course, use our solution KronosFlow for forward stratigraphic modeling that will allow you to have a very detailed sedimentology content and have a precise facies model that you can integrate within the section.
Thanks, Alcide. Actually, we have 2 more questions.
Oh, okay.
But I keep them because they're good ones. So first one is, if I understand correctly, the fault will be permeable if there is some displacement along the fault planes, and if yes, the displacement depends on rock stiffness and boundary conditions, such as tectonic strains. Do we use this information in the model?
So, well, the fault will be permeable when it moves. That depends on your interpretation. Marie mentioned that scenario before, but that can be one geological scenario, which is a classical one. But usually what you can say is that first you have nothing, so transparent fault. Then the fault moves, and you can assume that during the movement, the fault becomes permeable, but it may not be the case. And then you assume that when it stops, you may have some cementation and some closure of the faults. But this is, as I'm saying, it's one scenario. You may want to try something else with an early cementation of the fault, with some smearing effects, or you can just leave it open and just let the lithological variation on both sides of the fault just do the job.
Yes.
In terms of technical stress, maybe you want to add something on the first part, Maya?
Yes, I just want to make clear that there is no automatic computation of the fault behavior through time. You have your restoration, which give you some fault movement and fault timing. And by default, all the faults are considered as transparent. So as Alcide was just saying, they are juxtaposition interfaces with no particular flow behavior. And they put different types of facies in contact, different types and nature of facies in contact as they move. So this is the default case, and it's already very interesting to see what happens with that. And then you can complexify your model by putting some specific parameters for the fault, such as a permeable behavior or an impermeable behavior. And you can play with that around and see what happens on your model, what happens on your hydrocarbon migration, pressure compartmentalization, and so on. That was for the first part, and then for the stress, I let you reply.
Yes, no, for the stress, there is no direct impact of the stress on your faults. So as Marie said, everything is user inputs, but what you can do is, if you think that the behavior of your fault is related to the stress, you can actually do that in 2 steps. You can do first a simulation that will allow you to represent the stress through time and understand what it is, and as it is an output of the software. And when you reach a certain level, you can then go back to your input parameter and modify the behavior of the fault when it reaches a certain level of stress, and define that and use that as a constraint. But it will be manual, and then run a second simulation where you have taken that into account.
So another question related to compatibility with the other software and best practices in terms of workflow. Mm-hmm. If we are importing an interpretation from Move, we can have sometimes a lot of points. Should we delete them in order to have less points from the beginning?
Okay, so yes, indeed, I didn't mention that, but you can import your present day section from other software. So if you have it in Move, if you have it in Dynel, if you have it in Lithotech, if you have it in Kine3D2, you can import that within your software. And actually what we have in Kronos are several tools to check the consistency and validity of the section. So you can make sure that, first of all, everything is okay, if you have the right contacts and so on between your blocks. And we have an automatic option that allows you to resample your horizons. So actually you do not have to do that. You can just let the software do it. And by mentioning what is the sampling that you want, 1 point every 500 meter, every 1 kilometer, every 10 meter, which would be way too much, but you can actually give that as an input, and the software will automatically clean the section if needed.
Okay, that concludes the first Q&A break. We are at 37 minutes, Elcid.
Okay, so I will try to go actually relatively quickly through these case studies in both compressive and extensive settings. So the first case is actually a case from Bolivia. So here you have the present day section with 15 stratigraphic units, and these units present 3 main source rocks, which are represented here with that green color, so shaly source rocks, type 3 source rocks, and several main reservoirs also in the Devonian, which are here represented in orange and yellow. So once we have defined that present day model, we perform the restoration. So that restoration was driven by a balancing that was done before in lithotect. So we focus on that foreland basin right here, and I will just show you the last steps, because first we start with a simple deposition, and the movement of the blocks will start at 5 million years after a thick deposition of sediments. So at 5 million years, we have that thick deposition, and then each scale moves one by one until present day. That comes up with a very strong shortening of 31 kilometers. And once we have performed that restoration, we build a single grid that is continuously deformed through time. We then launch a first temperature simulation in order to check and calibrate the model in thermal condition through time. So we validate it through a comparison between the simulated data and the observed data at well location in temperature and vitrinite, and we obtain a good match. So this results in that level of maturity for the source rocks. So here you see actually the vitrinite reflectance for the entire model, and the 3 source rocks are here highlighted by these stars, and you see that here they are mostly within the gas window everywhere, and you can also see that we have that nice repetition of vitrinite reflectance features. So how does that translate in terms of generated hydrocarbon? So we see that through time, we have a first phase of generation, which is quite simple, that only comes from the burial of the basin, the constant sedimentation, and then at very close, so at very recent time, we have a strong peak of generation and expulsion, which is right here, and mostly for the upper source rocks. So how does that translate in terms of migration? So initially, we have very little expulsion from the source rocks. Everything is flat. And then when we reach the movements, this is when we start having migration. And we see that we start accumulating within either a stratigraphic trap underneath the fault or within a structural trap here at the top of the anticline. And this is here the situation at present day that is summarized here. So we identify several accumulations. And what is interesting is that some of these accumulations result from remobilization. So here, if we look at the last time step, here you see that we, at 3.7 million years, we had that accumulation right here in that little anticline. And actually with the movement of this block on top of this one, you see that the reservoirs that were in contact here on the side are now in contact at the top of the structure. And that allowed the hydrocarbon to migrate, to dismigrate into the top of the structure here and a little bit in that structure over there. So that is very interesting to see that we can properly represent the migration of the hydrocarbon through time through the proper representation of the migration pathways. So the final accumulations that we are these. So we have 2 main accumulations that are actually known fields and that allow us to validate and calibrate the model in terms of saturation presence. So these are known fields that are produced, that were produced at the moment of the analysis. These 2 were actually prospects that were already identified, but that have been validated by the model. So the study was actually done in 2018 and they validated these 2 prospects and they were drilled in 2019 with success and with the right representation of the hydrocarbons. And finally, here under the fault, we have a new carboniferous plate that was not identified before the work and that should be further investigated in the future. So here we have seen how a compressive system can be represented, but this case from Canada will also show us how this new workflow can be interesting even in an extensive setting, as we are able to properly represent the impact of the fault on the overall pressure field and migration of the hydrocarbons. So this is the present day model with many more layers and a certain number of faults. And here you see that we have a very nice description of the lithologies with the lateral variation of clastic sediments, so from sandstone to shale. So the restoration was done with the guidance from 7 restoration steps done in Lithotect. So the section was balanced at present day, and we used the paleobathymetry of every time step in order to drive the restoration within KronosFlow. So this is the resulting restoration here through time. So everything is quite classical at the beginning. So we have a simple burial. And then what is interesting to see is that at between 34 and 30 million years, we have a destabilization of the platform and the creation of these extensive faults right here, and that compressive system at the bottom of the platform. And then until present day, we just have a normal, I would say, burial again with a little bit of movement along the faults. So how does that translate in terms of pressure regime? So I skip the maturity part because we've seen it with the Bolivian case, and here I will focus more on the pressure. So here we have the representation of the overpressure. So before the movement of the fault, everything is similar. And once the fault becomes active, this is where we will see a difference between the two scenarios that we have here. The first one is a transparent behavior of the fault. So we just let the juxtaposition of the lithologies on both sides of the fault play their role. And on the second scenario right here at the bottom, we suppose that the fault become impermeable straight away and that no flow is possible between the different fault blocks. And so this is the behavior that we have through time. So at the top, we see that things are quite homogeneous, when at the bottom, we see that we start having compartmentalization and with a strong difference of the overpressure between the different fault blocks. So that means that if we decide to drill in one part of the section, we know what level of overpressure we can expect. And here at the top, we have our best case scenario, when here at the bottom, we have a worst case scenario. So as we have only one well, which is located on the platform to calibrate the data, both scenarios are equiprobable and are valid. So here the calibration is actually the same in the two cases and is good in the two cases because the well is far enough from the faults for it not to be impacted by the fault behavior. So both scenarios are equiprobable and they correspond to a best case and worst case scenario. This is the resulting hydrocarbon saturation that we obtain. So this is for the case with transparent faults, and we see that we can identify several accumulations of interest within the basin. And these accumulations, as we run a scenario which is multi-compositional, so with different fractions, we can have the description of their quality content. So we know what is the gas-oil ratio. We know what is the phase, what are the phases that are expected within the accumulation, so either oil or gas, and we know what is the API degree of the liquid phase within these accumulations. And finally, we can actually compare the behavior of the hydrocarbon migration through time, depending on the scenario. So here transparent faults, here impermeable faults, and with the movement of with the movement of the blocks and with the migration of the hydrocarbons, here what we observe is that with the transparent fault movements, we start having an accumulation here that is bigger because all the hydrocarbons on both sides of the anticline were remobilized, when here they were trapped in the different fault blocks. So actually here the accumulation is smaller. And same thing here, we have a compartmentalization of the accumulations when here everything is remobilized and is moved to the top of the structure. And until present day, here we will see that we have several scenarios. Here we have a stronger disintegration of the hydrocarbon, when here everything was kept within the structure, but we actually see that the expected accumulation in that structure is very similar. But in other areas, here we have an accumulation that doesn't exist in this case, when here we have an accumulation right here that doesn't exist in this case. So here you see that you can have same thing, best case, worst case scenarios, or you can also validate one of your scenarios depending on the knowledge that you have on the existing accumulation. So for example, if you have drilled here and you know that this accumulation needs to be represented, it means that this scenario is correct and this one is not correct. So just to give you some ideas, here are the figures. So we know that for you to have an idea of how long it will take to get these models. So the whole restoration takes 1 to 3 days from a balanced section. So that will of course depend on the section complexity and the knowledge that you have of the deformation scenario. The generation of the mesh is instantaneous. And then the simulations just take a few minutes to run. So from 2 minutes for a temperature run to 8 to 15 minutes for a migration run. So it never takes too long to run the simulation, and it's very quick and easy to test various scenarios. So overall, the total study time will take from 1 to 2 or 3 weeks. And that will of course depend on the area complexity and the objectives to reach, and the number of scenarios that you want to test, and the difficulty of calibrating the model as well. But it will take actually a very similar amount of time as for a classic basin modeling study, but taking into account way more elements. So that concludes the example section. So I don't know, Marie, if we have any questions.
Well, no questions. Oh, yes, one, right in time. How can we reproduce the same thickness of erosion events from balanced sections from Move, Dynel, and other packages in Kronos?
Well, you would just do it the same way. I mean, so here, yes, what you cannot reuse past paleo sections within Kronos directly. So you have to redo the restoration. But what you can do is you can actually put in the background an image, so a PNG, a JPG, or bitmap, or whatever. You can put an image in the background of your section when you perform the restoration, and you would be able to draw exactly the same amount, the same quantity as what was estimated within Move or Dynel or whatever it is. So here you can very easily reproduce the quantities and the geometries that were done in other software packages.
Okay, that's it. You can go on with the demonstration.
Okay, so let's go to the demo. So
10
I will
minutes left.
Sorry?
10 minutes left.
So now you should be able to see KronosFlow, so which is part of the OpenFlow suite. And the idea of that demo is to show you the entire workflow from A to Z using a simple section, because if I want to show you everything, I will have to, I need to use a simple enough section to do so. So here we start from the digitalization at present day. So the present day section that is already defined. So you see that we have several horizons, several features here that were defined, all the faults, and these horizons actually correspond to that stratigraphy that is right here. So when you have drawn everything, you can check that the contacts are okay. You can check that your stratigraphy is good, that you do not have any small areas. And here you can see it's where you have your point spacing, so where you can define the number of points you want to consider for each horizon. So here we consider a point spacing of 500 meters, and we can create the model. So then we move to the section property step. So here we started from digitalization, we move to section properties, and this is where we are going to define the stratigraphy. So you see that by default, the stratigraphy is properly defined, except in some patches that we can redefine if need be. So for that, you just select the patch and you drag and drop the stratigraphy information that is missing. Or you can use that table right here to automatically select all the patches at once and drag and drop as well the information. or define it through a right click. Once the stratigraphy is properly defined, you can define as well the lithology contents. So this will be done the same way. You select the unit from the table, and then you drag and drop the lithology content from that table right here. So for the crust, we use some upper continental crusts. The lower Jurassic will be our source rock, so we drag and drop some shale. I will zoom in for you to see it better. For the mid-Jurassic and the upper Jurassic, we just assume it's a mix of classic, so 50 sand, 50 shale. The lower Cretaceous will be our reservoir layer, so some sandstone. The upper Cretaceous will be the seal, so it's a shaly layer as well. And the most recent section will be just a shaly units, 30 sand, 70 shale. So here we have defined the lithology with a continuous lithology information over each section, but we could, of course, have something that varies laterally. I'm not going to spend too much time on that right here. When everything is okay, you can validate the present day model and move to the restoration step as shown up here. So here, what do we have? To the left, this is where we can select what we want to display. So for example, we can add a background mesh in order to properly represent what we want. We can select if we want to display the age, the facies, or the fold blocks. So for you to understand here, the fold blocks are defined by the different folds of the model. So here we see the different fold blocks. And to the right, we have all the deformation methods. So let me show you the main deformation methods. So let's start with the sliding option. So where we have one block sliding on top of another. So for that, you just select the block, you move it to wherever you want to move it, and you drop it, and this is a deformation. You see that every deformation step is saved here, and you can go back to a previous step right here and try something else if you are if you want. So here, let's try a different deformation engine. So we select the mode and then the engine. So the first one was moving this square. Here I'm trying flexural slip, and I can try the different modes. So I can go either backward or I can go forward like that. If I'm not happy, Control Z to undo works as well. The second deformation method is with two constraint lines. So here I was just using one fold, but if I want, I can use, for example, a palobathymetry, so that I will draw quickly right here. And I can drag and drop the blocks. So I will just remove the top units to do that deformation. So I will do it with a moving list square here. I drag and drop the block. And here what you see is that the deformation is applied using the palobathymetry as constraint. So how does that work? You see that when I select the block, I have a blue line and a green line that appear, and I get close to the palobathymetry. The palobathymetry turns blue to tell me that this is that constraint that will be applied to the other one. I can do the same for this block. So here you see I have blue and green. Now when I get closer, here I have two constraints. The green corresponds to the folds, and so the top fold becomes green, so it's the target, and the palobathymetry becomes blue, and I can drag and drop it. And here you see I have some block restoration, and I can check if everything is correct in terms of balancing. And so I can keep going like that for the blocks. So here you see how I can use two constraints. And finally, the last deformation mode that is available is deformation where you can constrain all your horizons, and you can say that actually every horizon will match perfectly the horizon on the other side to perfectly restore the folds. So this is what I'm doing here. I'm matching every horizon with the other one, and with a right click, I can perform the deformation and have a perfect restoration here of the folds. So let's actually go back to present day, to the initial stage, and do the right deformation that we are supposed to do. So here what we want to do is actually move all these blocks at once and restore the first fold throw. So for that, we actually here within the fold contacts define all the folds inactive except F1. So here we change our fold blocks. So you see we have only two fold blocks now. And I can here select the deformation mode, which will be sliding with a flexural slip. And what I want to do is I want to restore the fault along the top of the green horizon. So I do that. Here I have the proper deformation. And then I can draw the missing material, so the erosion. So for that, I will extend the fault right here and draw the fault. The missing material. So sorry, until the fault. So here, extend the fault again, draw the missing material. Okay. And then I can close the final gap right here with some missing material as well. So here you see how I have restored that block and added some eroded material. So that corresponds to the second step. So here that is the step at 5 million years. So I want to save that. And these are the steps that will actually be sent to the calculator. So I click here to create a key deformation step. 5 million years. I can here take into account the decompaction or not. So here I will take it into account. Okay. And that will create a new step at 5 million years from the step at 0 million years right here. I can here continue. So for that, I will actually just move to that model where everything has been done. So you see here the full restoration with the different time step and with the proper restoration of the entire deformation. And once you have performed the whole restoration, you can actually mesh the model. So that will be done through the scenario manager that here shows that restoration tree, where you make sure that you have selected the right path, which is this one highlighted in green, that you can mesh right here. So here you are in the meshing tool. You can here define the resolution of your mesh. So here I will put a resolution of 300 meters. So this is the mesh that is generated. You see it's a unique mesh, it's instantaneously defined, and it follows the deformation through time. And you can send that afterwards within ThemisFlow for the basin modeling purpose. So here you create your ThemisFlow scenario. I will name it Chartreuse Demo and click on Finish. So now I am ready for the basin modeling part. So I will just close all that and move to the basin modeling parts. So this is it. So here I have the scenario that contains the model, which is right here. Everything is ready for me to define all the information that I want. So I already have the restoration through time that is already there. I already have the lithology content. So what I need to define is only, in that case, the source rock content. So I will define the lower Jurassic as a source rock, define the kerogene, and define the TOC content here at 4%. I check everything to make sure it is okay. I can save it. Okay, I bring a geochemical library to define the kerogene behavior. And I will here define the type of simulation that I want to launch, which will be decoupled Darcy flow, so full migration simulation with a 3-class scheme. So here I can save everything and I can launch the simulation. While the simulation is running, let me just show you how we define the faults. So here within the fault properties, so you see that the faults here are highlighted, and you can here within the fault properties for each fault define their behavior through time. So this is here, and I can say that, for example, the fault F1 at 5 million years, it becomes either impermeable. So in that case, the factors will be set to 0, or I can make it user defined. And in that case, the permeability will be set to 1 in terms of factors. So I can actually close that. And you see here, sorry, that of course these can vary through time. So I will close it and go back to the simulation. So here the simulation is running and it will be finished shortly. So it will take normally just a few more seconds. So you can see here, you can see it progressing right here. Okay, so here you see that the simulation ended in 60 seconds, so in just less than a minute. Now the results are being re-imported, and when the results are imported, they will be here present within the ArcTem simulations panel. So here you have them. You have all the results. So let's have a look. I can have a look at the vitrinite reflectance. So for example, easy RO. So this is what it looks like at present day. And I can have a look as well at the saturation, H liquid saturation, which is right here. I can have a look at that at present day. So here I can identify some nice accumulations, and I can of course see their evolution through time. So with the feeling of the saturation of the traps, and here identify some structural traps or some stratigraphic traps, and I can actually have some information on their contents by showing here composition and HC composition right here, which will give me here a reporting that tells me what is the composition of that accumulation, and here I will have some information on the pressure within the accumulation and stuff like that. That will be interesting to properly characterize and rank the different accumulations. So I think that concludes the demo. I don't know if we have any questions, Marie, on the software.
I'll start with a question related to the mechanical properties of faults. Can we use characteristics such as friction along the fault plane? Because the plane with less friction will have more values of displacement than the plane with high friction.
So unfortunately not. Right now, we do not take into account the friction within the displacement. So
yes, once again, fault displacement, it's really driven by the restoration itself, and so it's really user guided.
Yes. So if you have a software that allows you to take it into account and to estimate it, you can actually drive the movement of during the restoration. You can drive that with the model, and if you have some friction information, you can integrate that as an input parameter, but you will have to manually define it within the editor that I showed you and say, okay, at that age, because I know there is friction or I know there is not friction, then that will be the behavior of the fault, but it will not be automatically done by the software, although you can integrate it and consider it if you want.
And to finish, last question, is KronosFlow available for 3D modeling?
So unfortunately not as well. So right now KronosFlow is a 2D restoration tool, but in Basic we offer a full 3D workflow, although it is way more complex. So actually the calculator that I show you here works the same way on 2D models or on 3D models. However, the complexity in 3D is to generate a 3D grids that is restored through time and with a continuously deformed mesh. So today we do that with Kine 3D3, which is a software from Emerson, formerly Paradigm, and that requires a lot of expertise. So it's a work that is very, very hard to perform and that sometimes cannot comply with industry standards, and it may take a lot of time. So it is possible, it is doable, but know that if you want to do that kind of workflow, you should allow several months in order to be able to do it.
Yes, it's more of a prototype for now. So sorry, we have an avalanche of questions to finish. So related to that, is it possible to reproduce pseudo 3D models using a set of restored sections? So absolutely, that's a very good idea, and it's actually a workflow we have experience with the customers. So you can perform several sections in parallel and in different directions in order to capture the 3D potential of the area. Can the model include intrusions in terms of kinematic and thermics?
So you can actually have some lithology changes through time. So that means you can change your the petrophysical behavior of your rocks. Unfortunately, not for the moment. The thermal intrusion is not available for that kind of workflow, but it should be available soon. But right now, it's not available in the software.
And finally, do we have a specific easy RO function?
So yes. Here we have an integrated EasyRO computation that takes into account a certain kinematics, so time and so on. But you can have actually the possibility to tune your vitrine reflectance to the behavior of a given source rock by defining a law of transformation ratio versus vitrine reflectance. So you can actually define any vitrine reflectance law that you want compared to a given kerogen within the geochemical library.
All right, that's it. Thank you all for all of these questions. It was a very rich session.
Yes, thank you
for
very
your
much.
participation. Olga, maybe you want to say something
Yes.
to finish?
Спасибо вам большое за то, что приняли участие в нашем вебинаре. Надеюсь, он был полезен. Кто-то, может быть, нашел для себя что-то новое, кто-то, может быть, задал какие-то вопросы, которые интересовали. Есть какие-то вопросы или, может быть, что-то интересно, подробнее вы хотели бы обсудить какие-то примеры или, может быть, какие-то функции? Ждем ваших вопросов на почту, на телефон. Пишите, звоните, с радостью будем отвечать на них. Спасибо большое всем за внимание.
Спасибо.
Bye-bye.